Look at your phone. With a single tap, a blue dot appears on a digital map, pinning your exact location down to a few meters. We take this for granted. We treat it as a localized feature of our handheld devices, a simple utility embedded in a microchip. But this is an illusion. The blue dot on your screen is not calculated by your phone. It is the real-time manifestation of an invisible, highly synchronized cosmic infrastructure. At this very moment, a constellation of at least 24 operational satellites is screaming through the thermosphere at 14,000 kilometers per hour, roughly 20,000 kilometers above your head. To tell you where you are, these machines must continuously broadcast a precise record of time across thousands of miles of empty space. If their synchronization fails by even a single microsecond, your location on Earth shifts by hundreds of meters. Navigating a modern city would become entirely impossible. The technology inside your pocket doesn't just communicate with outer space. It requires us to alter our fundamental understanding of time itself. To understand how this system operates, we must first look at the pure geometry of location. Imagine you are lost on a completely flat plain, with no landmarks to guide you. If a single satellite tells you that you are exactly 20,000 kilometers away from its position, you haven't locked down a single point. You know you are somewhere on a massive circle. Now introduce a second satellite into the equation. It broadcasts its own distance signal to you. It tells you that you are 21,000 kilometers away from its specific location in space. Two circles on a flat plane can only intersect at exactly 2 points. Your options are narrowed. You have narrowed your existence down to 2 distinct coordinate options on the map. When a third satellite joins the network, its signal provides a third geometric circle, which intersects perfectly with only one of those 2 points, eliminating all ambiguity. In our real 3-dimensional world, these flat circles expand to become massive intersecting spheres. 3 intersecting spheres pin your position down to 2 points in space, but one is in deep space, leaving only one logical location: your exact position on the surface of the Earth. But this clean geometric engineering model immediately collides with the chaotic nature of our universe. Enter Albert Einstein. In 1905, Einstein published his revolutionary special theory of relativity. He demonstrated that time is not an absolute ticker tape running at the same speed for everyone. Instead, time is entirely relative to speed. The faster an object moves relative to an observer, the slower its internal clock will tick from that stationary observer's perspective. This physical phenomenon is known as velocity-time dilation, expressed clearly by the Lorentz transformation factor. GPS satellites travel through space at a constant velocity of roughly 3.9 kilometers per second. To an observer standing completely still on the surface of the Earth, the clock on board that satellite is moving fast enough to experience this relativistic slowdown relative to ground-based time. The temporal difference seems completely minuscule. It amounts to a loss of approximately 7 microseconds every day. 7 millionths of a second feels irrelevant to human life. But satellite signals travel at the speed of light. if we completely ignore special relativity and leave the satellite clocks unadjusted, that tiny 7 microsecond lag translates into a massive distance calculation error of over 2 kilometers. Every navigation system on the planet would drift into total uselessness within a matter of days. But velocity is only the first half of the problem. 10 years later, in 1915, Einstein expanded his work. He introduced the general theory of relativity, altering how we perceive gravity itself. He showed that gravity is not a mystical pull across space, but rather a structural warping, a geometric warping of the very fabric of space-time, caused directly by mass. The closer a clock is located to a massive object like Earth, the deeper it sits inside a gravitational well. The deeper you are trapped inside a gravitational well, the slower time moves relative to outer space. Because GPS satellites orbit 20,000 kilometers above the Earth, they experience weaker gravity. According to general relativity, this significantly weaker gravitational pull causes those satellite clocks to tick faster. The exact formula governing gravitational time dilation dictates a clear mathematical acceleration in space. When you calculate this specific environmental effect, you discover that the satellite clocks gain 45 microseconds daily. Now, we must look at the net effect of both theories combined on the system. Special relativity slows the clocks down by 7 microseconds per day due to velocity, while general relativity speeds them up by 45 microseconds per day due to altitude. 45 minus 7 equals 38. The net result is an operational gain of 38 microseconds. To make GPS work, engineers had to deliberately program the satellite clocks to tick slower before launch. How do engineers maintain this extreme level of temporal precision in the harsh environment of space? They don't use quartz crystals. Inside every satellite sits a suite of ultra-precise atomic clocks, typically utilizing the highly predictable natural quantum oscillations of cesium-133 or rubidium atoms. An atomic clock works by exposing these specific gas atoms to highly targeted microwave radiation. When the microwave frequency matches the exact quantum transition state of the atom, it absorbs energy. For cesium-133, that transition frequency occurs at exactly 9,192,000,000 Hz. By using an electronic feedback loop, we create a clock that won't lose a second in millions of years. But even these flawless quantum machines require constant ground support to survive the volatility of orbit. Solar radiation, extreme thermal cycling, and minor orbital deviations can still cause minuscule time drifts. To correct this, a global network of secure ground tracking stations continually monitors each satellite's broadcast. Twice a day, these ground stations calculate the minute orbital shifts and relativistic deviations precisely. Then upload these vital correction commands directly back up to the constellation overhead. When your phone receives signals from space, it applies these uploaded corrections via software algorithms, ensuring that the time data used to build your location coordinates remains completely flawless.
Data stream flawless.
The next time you open a map on your phone, look past the simple glass screen. Consider the profound convergence of human ingenuity required to keep you from getting lost. To pinpoint your vehicle on a city street, we must choreograph a complex ballet of orbital satellites, flying through a harsh vacuum at incredible speeds, thousands of kilometers above our heads. We must harness the absolute quantum vibrations of radioactive elements locked in vacuum chambers. And, most remarkably, we must constantly adjust for the fact that time itself moves at a different pace. GPS is not just a triumph of digital engineering, it is an active proof of our deepest physics. It proves that the abstract equations scrawled on blackboards a century ago are the invisible machinery guiding us every day.